So, hello everyone. Welcome to our second lecture of ECS165. And today we're going to continue our conversation on sort of the high-level view of the relational system and the key components that included in the database. So let's get started. So this is where we ended last time, and the focus is just if you kind of look at a very high level, 1,000 feet above, and kind of say, what are the key components of any database system? One thing is the storage, and the storage traditionally is really the focus is on disk, on persistent, non-volatile storage. And over the years, the storage can be SSDs, it could be flash, it could be non-volatile memory, NVM, and sort of there is a wide range of there's essentially a hierarchy of storage and even your traditional tape. So that's storage. And of course, you still have your volatile memory as well. So the data will also be brought into memory. And so that's your in-memory storage, or often called the buffer pool. So that's one key component. The other key component of any relational system is all the indexes that you have. And of course, the indexes are also stored, often persisted, are in the storage as well, but you have specific facility that deal with indexing. And then there's your runtime. So the runtime, it takes a transaction from the client and does all the read-write operation necessary for that transaction, interacts with the indexes, interacts with the storage, interacts with the log, and it's just responsible for running the transaction. And if you're running analytical type of queries, there's a lot of query optimization and query planning, and query evaluation becomes much more complex than just reading a set of records or writing to a set of records. Then the other component is a log. And the log is, as what the name suggests, is just basically like a scratch book you can think of, or a bookkeeping journal that anything that we do, we'll kind of write it down. And we're going to talk more in detail why later today, but it's basically that we want to make sure any action that is taken are logged. Why? Because if we need to go back, we can decide which action needs to be perhaps removed, or which action perhaps needs to be re-executed, depending on the crash scenario that we may face. So oftentimes the log is necessary for recovery. The storage, the data is essentially a redundant piece of information. It's already stored in the log. Yet another redundant piece of information that we have is an index, because the information, we could always go back to the storage and get the information we want. You can really think about as log is the most basic information, which is just exactly every change or every transaction that was executed. And that is sufficient to know the state. So just having the log, I can go potentially, in the worst case, I can go to day one and figure out the balance of every person after recomputing all the transactions they've done, all the purchases they made, of all the earnings that they have. So you can always, based on the log, determine the state of every entity, or you can reconstruct the state. So that's log. So in terms of the storage, so talking really about relational model and tables and rows, so that's a more efficient representation of that log. So as opposed to I kind of go recompute and redo everything from scratch from the log, I have a more optimized representation. So it's just row and columns, it's just tables. I'm looking for one particular record. I don't have to find out the history of everything that was done to get to that point. I just go to that particular record and read it. And to do that, I may have to kind of scan the entire table till I get to that point. So it's much more efficient than a log. Now the index, as opposed to me going through look at every single record, if I'm looking at one particular person, I'm looking for salary for Alice, then I can just look up the index. From the index, I can just directly point to that record in my table. So again, it's another form of, it's another representation that allows me to do query efficiently. And we had the comment last week as well too, is that having these redundant representation of the data, it makes our read query much faster, but it makes our writer slower. The most optimal storage in terms of write is just writing to a log, just an append-only log. That's all need to be done. Adding the storage of the table and then the relational model, well, we need to write to a log, and then we also need to write it in that form. Having an index, we need to write to a log, write to a table, write to our index. So there's more and more that needs to be written. So those are the main components. The final component of any relational system is that, well, even on your phone, you may have 8 processor or 8 cores or 16 cores. And on sort of commercial or on modern servers, you may have hundreds of cores. And so that means in order to utilize this hardware, you cannot just execute one transaction at a time. Simply, it just doesn't make sense, because then, well, you're doing one thing at a time and there's hundreds of processors and cores and threads, physical threads that are just sitting idle. So it's not a good utilization. And especially it's not a good utilization because in the last 20 years, we've kind of stalled on increasing the clock speed. We really focus on increasing the number of cores. So doing a single task on a single core is not being improved because we hit the clock, almost hit the bound on increasing our CPU frequency. But so in order to really utilize modern hardware, we really need to make sure we know how to parallelize it and use many cores. So to do many cores, you need synchronization mechanism. You need to deal with race conditions, and you need to schedule actions that are non-conflicting. You don't want to overwrite one another. So, for example, if I check my balance and I see I have enough money, then I check there's a book that I want to buy. Well, the book is available, then I go get the money to pay for the book. And by the time that that action is taking place, I've already taken the money off of my account, and but somebody else has already purchased the book, for example. So there's a lot of conflict that could potentially happen, and the synchronization mechanism are the means to protect the correctness of the execution. And that's concurrency protocol. And what concurrency, as the name suggests, is that to be able to do things concurrently, simultaneously or concurrently. And that kind of wraps the picture, sort of which I think basic too, is a basic picture of what the relational system involves. As a storage, as a log, as a bunch of indexes, concurrency control, and a bunch of threads that actually, or the worker thread or the execution threads that actually do the actual work. And of course, we may have a client that submits the transactions. And this is what we're going to also build for your milestone. So we're going to go through all these stages. So any question at this high level view? Okay. So now, and slightly maybe even a deeper view, you have our database, or sort of our storage. You can think of it as on the lowest level. And then we have disk space management. So this is, you need a set of APIs that handles the file descriptors. How am I going to write to a page? What is the notion of a page? Who's going to take care of remembering if a table consists of a set of pages? Well, somebody needs to know, or there needs to be a module, a component that keeps tracks of that. So all of that could be pushed into the disk space management. And then on top of that, you have your buffer management. And buffer management is that, well, I know that I have a table, and that table consists of set of pages. And I know there's the page that I'm looking at, I know where it is, I can point to it. But for me to actually read it, I need to bring it into memory. And the buffer pool is essentially space that the database allocates in order to bring page in and out from the disk. And instead of just handing off to the OS and say, okay, let the OS handle the memory management. If I read a file, the OS just handles all the memory management. The database itself manages that because it knows which pages it may need in future. It knows which pages are better to evict if there is not enough memory when you need to read more pages. So it's a lot more knowledge that the database has, as opposed to an operating system just looks at software as almost a black box. So that's one aspect. And then on top of that, we have files and access methods. So this, the access method is really here. So we have an access control that kind of tells who can access what piece. Access methods tells us that, well, there are, for example, even in the previous slides, I said there are 3 ways to find a record. I can go to the log and rebuild the history in order to figure out what the value of a record is. Or I can decide to go to the table and scan all the rows and all the records to find what I'm looking for. Or I can go from an index, find the precise location of where that record is, and from there kind of jump to the page that maintains that record. These are 3 different access methods. And now, so that's the layer that deals with all these access methods. On top of it, we have sort of our relational operator. So for example, I can implement a join, or I can implement a filtering, a where clause, or a select clause, potentially by combining different or choosing among different access methods. So that's one layer higher. Now, the final layer is that to really talk about the query optimization and the query execution. And so given a query, if it's just get you a key or put get or put, then it's very simple. Like we can just even all scrap off the query optimization relational operator, because you just have an API access of gets and puts. To do gets and puts, I can go to access method and figure out what's the best way of getting that. So that could just sits at the relational operator level. But oftentimes we will have more complex queries that wants to combine multiple tables together and maybe do some aggregation. And so it's a complex operation. And so the query optimization execution, it kind of give it in a complex query. It sort of creates almost like a parse tree out of it, and then individually starts from the bottom and go its way up. So for this component of the query, you need to do a scan, then you need to join, and then just incrementally build all the way to go to the root, and then finally the result can be computed. So all of that goes into the highest level. For our assignments, we're really going to focus on the first 4 boxes, and our relational operator will be kind of simple. It's just get, put, scan, delete, and it's just basic set of operation. We're not going to get into that final layer of query optimization and query planning. So that becomes kind of outside the scope of or just a single 1 quarter. Of course, we're going to end the course with looking at languages and looking at the relational algebra and SQL, which kind of will look at some optimization as well. And by then you will have much better understanding when you talk about optimization, because you've implemented it, we've seen a lot of trade-off, and at that point optimization makes a lot more sense. So we're gonna leave that as the final topic of this course. And of course, there's a whole recovery on the side. See, there's no log mention of log here, and there's also concurrency. Again, there's no mention of it here. So those are additional component which we mentioned it in the previous slide. Okay, any question? Trying to describe it at sort of a high level in the most simplest way, that so that there are no kind of barrier to just getting a good comprehension and understanding of what entails in building a database system. And do you have a question? See one unmuted.
Yeah, I was gonna ask,
Yes.
so like in its simplest form, the relational operators is just the get put, whereas query optimization is parsing like complex statements among many tables.
So in terms of relational operator are actually sort of their select, join, the where clause, get and put. It is like a kind of a select, but get and put is even more primitive. So get and put are often using NoSQL type of environment, like a key value store. They're just, I think that the simplest, I mean, they're much more primitive. The relational operator, again, group by, join, selection. So they are more, they're more advanced. And in terms of the execution is that I can write a query that has 10 joins and 20, 30 different filtering conditions. So I need to break it into piecewise. I do smaller pieces and then kind of break it into small pieces and then start tying it together in order to form that complex query plan. And so that's that is the task of the optimization. And it decides, and there may be different ways. So for example, if I'm joining 10 tables, well, the question is, will I join the first with the third, or I first going to start joining the fifth with the sixth? So there's many different ways, or there's many different possible combinations, there's many possible paths to go. And each of them will have a different cost. And the optimizer, it needs to look at the possible, so look at the plan, to look at possible plan of execution. And usually this is NP complete hard, exponential in terms of the space of the plan that you need to consider. So it uses heuristic to reduce the set of plans that can explore. And then it reduces it to fewer set, and then it does cost-based evaluation, figuring out what is the cost of those candidate plan. And then it chooses a plan that is most optimal. And then sort of the node of that tree, once it figure out what that plan is, then they become SQL operation. And then from there, it goes to the access control. And then from then, it goes to file descriptor to kind of, or go to the buffer pool to you now get the sort of the base data. And it goes downstream and then goes back up the stream, go upstream.
Okay, I see. Thank you.
You're welcome. And again, so in terms of query optimization, we're gonna, again, so that will be essentially the last week of the class. Depending on how our timing goes, that's where we're gonna focus on that. But for now, for the remainder of the month and half or two, very basic API, very primitive API to get us the inner working of the database. And then one of the most important, in addition of the relational algebra, relational database, which is a very simple table and with a very simple set of operation, with a handful of operation and a table structure, it has been sufficient to pretty much cover majority, 80, 90% of all the use cases in industry for the last 50, 60 years. So it's really powerful, and that's the simplicity of the language and the simplicity of the abstraction. It has been one of the most important contribution in database theory and the database field in general. The other really essential piece is the data independence. And this again has resulted in the wide adoption, played a sort of a major role in the success of relational system. And relational system field, just looking at sort of the market capital, they're probably somewhere between 50 billion to $100 billion in terms of its worth. application in that space. So there are the data independence has two flavors. One is the logical data independence, and one is physical data independence. The physical data independence is a little bit easier to describe, is that when I create my schema, for example, when I create my student and enrolled schema that we had last week, as far as users concerned, I have a student class and I have an enrolled class. And I have also a courses class or a course table. So as long as the user is concerned, there's 3 tables. Now, if today the database decide to store this table as rows and columns, tomorrow decide to does it as trees, today decide that it's going to store the data only in memory, tomorrow decide that it's going to use both memory and disk, whatever decision that it makes, the database is independent of that contract almost, or in that definition of those 3 tables. So as far as the user is concerned, as long as the users can see 3 tables and can access these 3 tables, doesn't care how the underlying data is actually stored. So that's the physical that's the physical data independence. So the actual physical structure of the data. And that's really important because the database can continually becomes optimized, more efficient, and it doesn't really matter. The application doesn't really concern with those changes. It's not going to, every time the database needs to add a new kind of indexes, then the application also needs to be changed. So the application becomes completely abstracted from the underlying structure that the database maintains. So that's physical data independence. And that's the key sort of success for adoption, is that you create that interface, essentially your schema, that's the interface. And then as long as you can support that interface, as long as that you can stand to that contract that was made, which is your schema, then you can go ahead and make any changes you want to your application. You can go ahead and change anything you want to your database, and often refer to the database engine. So all the stuff that we covered, change your log, change your buffer pool, change your file access, change your disk access method. You can go change any of that and it doesn't affect the application. And so that's one thing. The other one is sort of more logical data independence, and that perhaps can be thought about as the notion of the view. So I may create a bunch of tables like student, enrolled, and classes. Then I may create a view that just is the subset of the student table, and it just maybe contains computer science. And it only exposes the name and the starting year of each student. So as long as the application is concerned, that's the view, that's what they see, computer science student, and he has 2 fields. Now, if I were to go and add more fields to that table or change the schema of that table, that view doesn't change. That view remains the same. So again, as long as the user views is satisfied, the actual set of tables on which the view is constructed upon can change. So again, that can be, again, it allows another level of independence. It's sort of abstracting out the lower level structure of how things are actually stored and accessed. And even you can abstract out the basic schema. And so you just provide to the user sort of a high level view that could be a narrower view, but that application, maybe that would be sufficient, because you could have a single database that supports dozens or hundreds of different applications. And so as long as you create perhaps a set of views for that particular application, then you have the freedom of, or the liberty to go ahead and change the overall schema design without breaking those applications that is built on those views. So that's another form of independence. Any question? Okay. So now it comes to the, I would say, one of the most exciting problems. So 2 exciting problems I think databases. One is data structures. So anything we talk about in database is always about data structures. how you store it on the data on disk, how do you store it in memory, what is the structure of your log, what is your structure of index, is all about data structure, data structure, data structure, data structure. That's probably one of the most important things. The second most important thing is when it comes to synchronization. And when you come talk about synchronization in the context of relational system, we really talk about concurrency control. So that's personally, these are my personal sort of favorite topics in database system: concurrency control and data structure, which is, well, how do you structure your data? And they're both kind of at the core or the engine, sort of the key component of any relational system. And again, we kind of talked about this. So there are two reasons why one would want to have concurrent execution. Because you can ask, well, why not just simplify things and I have a single execution? I answer one client query at a time, I answer one user at a time, and then I just simplify many things. Well, sure, that is a possibility, but historically, also I'll kind of talk about historically, I'm really talking about 20 years ago. So historically, the data size has been much larger than the size of the main memory. So then what happens, oftentimes your buffer pool was small. So that means every time you want to access something, you end up quite often you had to go to the disk. And it's very interesting is how long it takes to grab a data from disk versus how long it takes to grab data from memory. And Jim Gray, which also won Turing Award for his work on transactions in databases. There are several people who won Turing Award in databases. Jim Gray is one of them. And Codd, who invented the relational system, also won the Turing Award for his work in 1970. But Jim Gray has a very interesting way of sort of simplifying problem and explaining the problem. And so he has this nice analogy, which is actually the number. So the analogy in terms of its ratio is very accurate. So if I wanted to grab a book, I'm not sitting by my desk. I may have a book on my desk right now, which I do. And for me to grab that book, it's almost instantaneous. I could also want to grab a book, and that book is in another room. So I have to get up and go to that room. Or maybe I don't have that book. I need to go to the library and to get that book from the library. And he kind of expand on this example, and it says at some point the library doesn't have it, my country doesn't have it, I have to go to a different country. And then it kind of goes, well, there's only one library that has it, and that's on the moon. So I have to go all the way to the moon to get that book. And that's analogy in terms of the ratio of the efficiency and the speed. It actually maps nicely to the fact that if you look at the memory hierarchy, and where the memory hierarchy starts is that within the processor, you have a cache. And that cache is, you can keep minimum ones. You have an L1 cache, you have an L2 cache, and you may have an L3 cache. And so your L1 cache or your register, the time to grab a data item from there, and I'm talking about like 8 bytes or 1 word size, it might be 1 CPU cycle. Now to go to your second level cache, that may cost you 10 cycles. Now, in order for you to go to your, or 100 cycle. Now, in order to go to your memory, so the data is not the processor cache, you need to hit the memory, you could be in hundreds of clock cycle. And the clock cycle, we're talking about nanoseconds. But the moment now you want to go to your SSD, we're now talking about, no longer talking about just a cycle. And in terms of nanoseconds, we're talking about microseconds. The moment you want to go to disk, now you're talking about milliseconds. The moment you talk about tape, you're talking about seconds. So you're talking about 9 to 12 different zeros. So from the first to the end, you may have the numbers that you're dealing with 12 zeros difference. And that'll actually translate to those distances of grabbing a book from on my desk or going all the way to the moon to grab grab something. So, so that's very important, and everything we do in the database is we have to realize that there is this, although seemingly the hierarchy doesn't seem to be much, but in terms of performance profile, whether your data is in a processor cache, whether it's in your main memory, whether it's in your disk, or whether on your tape, huge difference. And now there's even more. It could be SSDs, it could be flash, it could be NVM, as I mentioned, and it kind of sits in a different location on this memory hierarchy. And so the whole set of trade-off. So now traditionally, if my data didn't fit in my main memory, I always had to go to the library to grab my book. Let's say going to a disk is like a library, for example. I always had to go to the library. Then for the time that I'm going to the library, well, nothing happens. The entire system goes idle. So it makes sense to, while for one query, I need to go to the library to grab a book, I start the next query and start the next transaction. Even if I only had a single processor, even if I had a single processor, it just didn't make sense to wait milliseconds for fulfilling a request while there's other requests that are there and you just don't take any action. So in the 70s, in the 80s, in the 90s, it was essential to be able to utilize the processor, even if it was a single processor, or if it was even two processor, to fully exploit this processor. And the only way you could do that is to have concurrent execution. So don't just take one request, take hundreds of requests at a time. And eventually have enough requests, you could potentially keep your CPU busy doing work, as opposed to your CPU just sitting idle or looping on just a random loop in order for the data to arrive. So that was the historical reason to necessity of be able to support concurrent execution. But now, as kind of explained earlier, even on your phone, you may have dozens of cores. So even if, so you must use it. So even otherwise, not only you're going to just be using one core out of all these possible cores. So just no longer going to utilize the resources, not just even utilizing one resources, but the rest are just sitting idle. So that's the necessity to do concurrent execution, is that to be able to either hide the latency of going all the way to the library to get the book, or because there's just so many other cores or processors available, well, and if you just have one user at one request at a time, well, all of them are going to remain idle. So concurrency is essential in order to develop a performant database system. And take the example of the book, you have to do interleaving of operations. So I said one request is sent to go get one book from the library, and I start doing something else. And then maybe this second request also needs to hit the library. So that goes to hit the library, the third request comes. And the third request comes, the very first request got the book from the library and it can start operating. So there's all these interleaving of operation, because no longer things are running in isolation, or no longer things are running single threaded. So things are running now concurrently. And then, so when we get to the situation when we don't have just a single thread, then of course we need to be able to make sure nobody steps on anyone's toes. And that's the job of the synchronization, and that's the job of the concurrency control. Any question? Okay. So, and we'll kind of now start defining what it means to have a correct execution. And the notion of the correct execution is really captured in the concept of transaction. And again, that's something that Jim Gray has done seminal work on this area. And one thing he looks at, it says, okay, why don't I look at historical interaction among people? Well, two parties would come together, and Kevin and Nicole, for example, they say, okay, they want to buy a book, or they want to purchase one thing from one another. And then what they do, they'll kind of, okay, I'll give you this book, and then you perhaps give me this this piece of fruit, for the sake of the example. So then they kind of write down these contracts. And so they now establish a contract, even if it's a verbal contract. And then the contract must have certain terms. Is that it can be the case that Nicole gets the book but doesn't offer anything in return. So either all the terms of the contract has to be fulfilled or the contract becomes void. So that was the sort of the number one thing that we start looking at contract. Now, if you want to digitize a contract, the one important notion of that contract, which we call in transaction, is that the transaction needs to be atomic. The transaction may have set of operations, and those essentially the steps of a contract that needs to be executed. And one key property of a contract or of this transaction is that either all the steps or all the actions of the transaction gets done or none of them gets reflected. So this all or nothing. So, and the notion is atomic. Well, assuming on the sort of again, another historic terms that the atom cannot be divided any further. So it's atomic, is all or nothing concept. And then the other thing that we talk about transactions. So now we have this sort of formal model, or you have this concept of transaction. And if I want to take some action, I kind of bundle those related action together, those actions that must be done together. So I can be able to emulate, or I can be able to simulate the same kind of transaction that one would do on a normal day-to-day. Now I want to digitize it, so I need that form of contract. And the other thing about this contract is that not only the term of the contract has to have the all or nothing property. I mean, of course, there's relaxation of this, but the base model is that all or nothing property. But also, we need to understand the effect of it on the system as well. And so the atomicity or the atomic is one key property of transaction. Another property of transaction is consistency. And consistency kind of has, unfortunately, multiple meaning depending on the context. One definition of consistency in this context is that if my data was in a consistent state before executing that transaction, and what consistent state means, it means all the rules and business logic or the application logic were satisfied before executing a transaction. After I execute a transaction, that atomic transaction, the database is still in a consistent state. So make sure that I don't apply transaction that just invalidate my data. A simple example is that I could have a constraint, and in order to define constraint, in order to define consistency, we define constraints, we define set of rules, and or also called the integrity constraint, is that, for example, say, well, it's a bank application, and there's accounts. Well, I cannot have negative balance, because I cannot spend the money that I don't have. So one consistent state, a consistent state could say that all the accounts, all the balances must be greater than zero, equal or greater than zero. So any transaction that tries to withdraw money that overdraft, then that would violate this state, and that transaction will be rejected. I want to buy something with my credit card and I surpass my limit, and that transaction gets denied. That's the basic concept of consistency. That's why that transaction is getting denied, because the consistency of the database was rejected. The transaction was one atomic step sent to the database, the credit card was swiped, not enough balance, you get a trigger and gets rejected. And that's exactly what is happening in that scenario. And so user needs to define these constraints, and then and at the end of the day is their user job, is the application. As part of it, when I design my schema as a database administrator or the application designer, I need to know what are those constraints are. And well, for the banking application is the balance example. For the airline is that you can't sell, if your seats, you've already filled up your plane, you shouldn't be overselling your seats, because, well, people can't stand on the aisle when the plane takes off. So again, this is highly dependent on the actual application. Or if you're Amazon, you can't sell a book that you're already out of stock. Again, so that could be a rule for a shopping cart or for a retail inventory. So again, those are something that is defined, but what the database provides the context, provides the semantics, provides the means to define a transaction, to make sure that the transaction is done atomically. It also provides the facility to state these consistency or integrity rules. And some application may use the database facility to check for these integrity constraints. Some application or some program, they may have, let's say, a cert condition in their program to ensure that some of these integrity rules are satisfied. Of course, storing a database has advantages, also has some disadvantages as well. Oftentimes, it's just performance. So those are two key concepts in terms of the semantic and the concept of transaction. Again, we're gonna this transaction is focus of our third assignment. And so we're gonna, again, go in a lot more details on other properties and kind of we will review these later again. But again, now is a good point to kind of have that sort of the broader perspective of where we headed. Any question? So now we're talking about concurrent execution, and we're talking about race condition. What does it kind of really mean at the high level? And the CC is the concurrency control. So there are, generally speaking, there are two modes of interleaving concurrent transaction. One basic one is, which is the pessimistic validation. Before I access any record, I'm gonna lock it. Now, how the actual lock is taken, what kind of lock is taken, those are sort of details. But generally speaking, one way of doing transaction concurrently is that any resource, any shared resource that others may be wanting to access, before I access it, I lock it. Once I lock the resources that I need, I can go read, I can compute any logic that I need to do. For example, I can read salary and increase the salary of every employee by 10%. So reading the salary is the read operation, 10% raise, is dependent on what was read, and then write it. So I lock all the resources that I need to make sure I'm having an exclusive access, do my read, do my compute, do my write, and then I commit, I finalize. If I can't get all the resources that I need, I cannot lock them, well, I'm gonna end up aborting. If I were to do my read, I'm able to do compute, I try to write, but then I see I violated some of the constraint, I abort. Only when I be able to do all of these without violating any constraint, then I can commit, and then I would release the locks, release the resources. And that's essentially what really just happened, is that said, if I'm the only user running, accessing the data, I essentially have the lock on the entire database. That's what it really meant. Single serial execution, what it really means is that I locked the entire database and I'm the only user. But then, in addition to the fact that, well, because of the interleaving operations, or because of the memory hierarchy, or because I have all these cores, those are all justification why it's not a good idea to lock the entire database before I do my actions. But there's also another thing, is that typically transaction is not going to touch every single record. When you go on Amazon, you're not going to buy the entire Amazon. You're going to buy maybe a book, maybe you're going to buy some other goods, but you're just going to buy a few items. So it doesn't mean that Amazon says, okay, nobody's going to touch my warehouse. I have a customer on board. Nobody touches anything. All the employee don't touch any shelf. There's one person who wants to buy something. In reality, that's never the case. And so that means I could just have the user just lock whatever they need, And as far as they're concerned, they're essentially running in isolation because everything that they wanted, they have full exclusive access to, and it doesn't matter if other transactions are running, because as long as they are not touching the same data that I want to modify or read, then it doesn't really matter. So locking does provide, essentially gives an isolation. It allows each transaction, although running in concurrently, but they're actually isolated. It creates their own island. This is my piece, and let me work on my own space. And as long as you hold that space by locking it, nobody's going to bother you. So you're in your own space. And as long as these space, all these spaces are non-overlapping, then everything can go successfully, non-conflicting through. Of course, there may be the case that there is really this hot topic. There's this book that everybody wants it. And so everybody trying to buy the last copy. So in that case, then there will be some delay, and you want to request a lock and you have to wait till it's released. And by the time it's released, maybe that book is no longer even available. So that's also a possibility. But in general, that's not the expectation. So that's one mode of doing things. The other mode of things is that more on the optimistic case. It says, well, why don't I just go read what I need to read and then do my compute, my logic, and then just figure out what is it that I need to write down? What would be the outcome of my transaction? And the modification that I want to do, I could either allow others to read those modifications, or I could say, okay, I know what I'm going to modify. I know what the new results that I want to write is, but I'm just going to keep it to myself. I'm not going to share it with anyone yet. So I'll do my read, I do my compute, I do my sort of locally write, is not visible to others. Then I do an optimistic validation, which is basically, once I did all the steps of my transaction, I just go ahead and do another read to make sure, or do another check of the database, make sure the book that I wanted to buy, there's still some available copies, and or the money that I want to use, I still have some fund left. And then I kind of post retroactively once I did all the actions, then I just validate whether my actions are still valid. And their action is valid is contingent or is dependent on what I read initially. So as long as what I've read initially is still valid right now, then I can go ahead and commit my transaction. So that's two modes, sort of very generally speaking, is of looking at concurrency protocol. So a way of concurrently executing transaction. You can take a pessimistic approach to make sure you're always on a safeguarded, what you've touched, you have exclusive access to. Or you could say, well, I think there is 50,000 copies of this book, and I don't think more than 100 people even going to buy it at a time. So why not just let everybody buy it, and in the just before I commit, I kind of just make sure that there's still some copies left. And as long as that's true, then I can go ahead and successfully complete the transaction. So that's the second mode. Yes.
In which situations does the right differ for the optimistic validation?
Which situation the right differs?
Yeah, because you say the visibility of rights may be delayed.
Yes, excellent question. So I could make my right visible. So if I'm doing things optimistically, I've read something and I know this is what I want to write, but I still don't have any assurance that even my transaction is going to go through. Because by the time I do my validation, it might be the case that there was only one copy left and somebody already purchased that copy. So the write that I do it may not be finalized. So I have a choice. I could let other concurrent transaction to read my uncommitted write, or the rights that are not finalized. And if they do read it, then they also have a higher chance of failing, because if I abort, then definitely what I've written is going to be dropped, And whoever read that value also need to be aborted as well too. So it does create a cascade of aborts. But of course, you could say on optimistic ground, well, I'm going to succeed. And so whoever read what I read also going to succeed. Then, well, I don't have to worry about it. So that argument still holds as well too. And it's very situational. So there are workloads and there are part of the workload that may exhibit characteristic that's best suited for the optimistic concurrency, or they may exhibit characteristic that's best suited for pessimistic concurrency. And it's always a trade-off. When it comes to databases, there's never a clear cut. It's always trade-off. And I think that's what makes it, I think, also exciting at the same time. And that's, again, a very important question. Any other question?
Can I ask a question? If you, in the optimistic case, if you don't lock the database, what if after you do the validation and then someone comes in to commit, and then you, because you did your validation, so you commit again? Might that validate, like, do something that's like conflict, if in that case?
Yeah, so that's another good question. So, and you kind of going to get into a chicken and egg problem, is that in a sense that, well, I do my optimistic validation, but if I don't do any locking, I did my optimistic validation, but what if, and also remember, we're also doing multiple actions. So I may be doing multiple writes. So I check my first one is good, I check my second one is good, I check my third one is good, and I hit my fourth one, that's not validated. So I have to kind of go back and drop everything. But also might be that I check my first one is good, I check my second one is good, my third one is good, but I haven't checked my fourth one. But what if somebody goes change my first one? So, and then it becomes interesting. So so the optimistic validation needs to, so there needs to be some, often there is a mechanism of some form of a locking. And it might not be that I'm locking every single record, but I may be getting, for example, a single timestamp. I may get, I am going to, before I enter to a validation, I'm going to ask, what is the time right now, for example, just as an example. I'm going to ask, what is the time? So the time is 5 o'clock. And now I am going to validate, and I'm the only one who's going to be at 5 o'clock. Anybody else asks for what time it is, it's guaranteed to be 5 and after. No one is ever going to get 5 again. So I got exclusive access to the timestamp of 5 o'clock. Now I can see the database at 5 o'clock. I say, if I look at everything that happened before 5 o'clock, then I want to make sure that what I've read initially still, if I started initially at 4:50, and then I want to commit at 5, I kind of lock the time. 5 o'clock is my time, and I want to make sure what I did 10 minutes ago still applicable at 5 o'clock. And anybody else that, and then the transaction that I commit, the writes that I do, they're gonna all get a timestamp at 5. So all my changes, it's going to be visible to transaction that happens after 5 p.m. Transaction before 5 p.m. don't see any of my stuff because it was a future for them. It never happened. So now, since I know I'm 5 o'clock, any transaction, any write that I do, it's going to be guaranteed to go at 5 o'clock. And as long as I make sure whatever was done before 5 p.m. still doesn't violate what I've had read earlier, then that's good. And anything that comes after me, since they're going to get a timestamp after me, they will have to ensure that all my changes has to be visible to them. So then there's an interest. So, and then the notion of time becomes a very interesting aspect in order to provide correctness guarantee. And in fact, the notion of getting a lock can be think of as advancing the clock. So you could advance the clock once at the end just to do your validation, but also the fact of getting logs could be seen as advancing time. And in generally speaking, most of work when it's done with transaction, it really becomes, believe it or not, a question of maintaining a time. And how do I maintain a single time? Can I efficiently, the problem of transaction oftentimes can be reduced to the problem of managing a clock, managing the time in a distributed way. And a distributed way because I have multiple threads and each may have their own local clock. And as long as the clock is synchronized, then I can ensure there is synchrony there. But the problem with the transaction, oftentimes, that requires a little bit more thinking and more kind of background knowledge, but it is a very fascinating question. And now the question of the transaction, the question of the concurrency can be reduced to the question of managing time, synchronized time. And that's a very general, and it also has application in physics as well too, where there exists a global time, because if every time is relative to the event that is taking place, the notion of the global time, the existence of global time itself, it's an interesting question of relativity. So all of these conceptually come to the question of time. But that might be a little bit kind of outside the scope, at least what we're talking within this course. But I think it's fascinating. Any other question? And we will talk about optimistic validation. We talk about optimistic concurrency control. We're going to look at specific pessimistic control protocol, and you will implement them for also for your third milestone. So we will definitely cover these techniques as well too.
So I was wondering if we have a process at 5 p.m. and there's a timestamp for that, and any process that tries to access those same resources after 5 p.m. has to check the timestamp. How is that different from a lock?
How's that different from a lock? So that's a good question. So one is, if I were to hold the lock on this, then I wouldn't allow any operation to go through. Versus with checking the time, well, there was nothing that was blocked. Things were running. And I know I read it at 4:50, and I know I'm going to commit at 5. I just need to double check that at 5 p.m. still nothing has changed. Everything is still in a good shape. Then I can proceed. And so that means between 4:50 to 5, a lot of things did happen. Sure, you have to reevaluate. You have to go recheck. There is a cost of redoing it, but there was less blocking. Things could progress, especially if it's the case that transactions they're not really conflicting. They're kind of they're not really affecting one another. So then why go to the process of getting locked? And also, the process of getting a lock, you have to release it. That's almost like checking again. A release in terms of the mechanism, rechecking something as in terms of validation, you think of it, you have to read something. So now I'm rereading the value. Releasing the lock, I still have to go to that lock and release it. So there is an operation that's also happening too. So at the end of the transaction, at the end of the commit, I'm going to release all my locks. So there is an extra step. If we just really talk about just strictly in terms of the operation that is happening, there is might be almost equivalent to do a validation in terms of cost, not in terms of the aim. So there is more work needs to be done to release everything that I've held. So the question is in terms of the optimistic ground, well, I have to do that work. Instead of releasing the lock, I'm not going to hold any lock initially, and I'm just going to do more checks to see if what I've done before was good or not. So then that becomes a form of it, again, as another trade-off. Does that answer your question, Kevin? Any other question?
I've got kind of one quick one.
Sure.
Will you see like a hybridized approach where maybe you start off with a pessimistic validation for a set amount of time, and if you're taking too long, they kind of open it up? Optimistic?
Absolutely. Yeah. That's very, I mean, that's kind of right on. That's a very exciting area. Especially now you can say, I think it was last week too, that was mentioned that, how about like machine learning model? Is that if I can predict, so it was a question, I think it was machine learning sort of predicting the read and write accesses of what I'm going to be reading, so I can make sure that I bring that data into memory. So I could also predict, this is going to be a hot record, and that's the terminology it's used. Let's talk about temperature of the record, for example. So if something is cold, it's not too many people accessing it. Something that is hot, there's a lot of friction, a lot of access on it, so it's hot. So if something is hot, then maybe I want to do a lock on it, because I know if I read it, I'm guaranteed to be overwritten in a very short amount of time. But if it's something that it's not frequently accessed, it's a cold record, then maybe I can just go ahead and optimistically read it. And so there are some recent work that have tried to incorporate a machine learning model in order to decide, or in order to switch between pessimistic and optimistic. They haven't really got a lot of adoption, because there's too much statistics you need to maintain, and it hasn't been as successful than one would imagine. But I think still at very early stages. Some of the work that I kind of done myself in this space when I was at IBM Research, in terms of supporting pessimistic and optimistic. So we look at a model that allows us to do both simultaneously. We didn't talk about whether the transaction should run on pessimistic or whether it should run optimistic, or just kind of looking at the interaction, because you now have to deal with much more complexity. If some transaction are doing locking, some transaction doing validation, you have to make sure everything can still run correctly in code. So there must be some coordination among these different kind of mechanisms. So we've looked at that. So that's a much easier problem. It's a much cleaner problem than trying to decide when to switch over from one model to another. University of Chicago, there are a few works, I think from there, that's I think interesting that they look at that problem. So, and then again, this what we talked about, this pessimistic, optimistic, is in a sense a form of a scheduling. So when deciding when to run the when to execute, when to take logs, or when to validate, and when to do interleaving of operation, these are all talk about out scheduling. And in concretely, when you talk about transaction, especially when it comes to the correctness of the transaction, the golden standard, the golden truth is that, how am I going to say, if I were to interleave operations, whether what I executed is correct or not? How am I going to reason about correctness of execution? And it's very clever the way that it's defined, the notion of correctness of execution. We know if I were to do things serially, single request at a time, things should be correct. Of course, as long as they satisfy the requirement, the constraint. Seems very straightforward. If I do things serially, then it should be correct. But when I do things in concurrently, I do a bit of this and then a bit of the other transaction, a bit of the other transaction, then how do I define the notion of correctness? And the clever thing in the transactional theory, or the serializability theory, is that if I were to schedule an interleaving schedule, I kind of just do all these things concurrently. And I do that, I go through it and do that schedule. I construct, I do things in a certain way, and well, it ends up to be some order that I did things. And let's call that a schedule, that final product. Now, if I take that schedule and I can map it to some form of a serial execution, then I can say that schedule was correct. So if I interleaved transactions I have 4 transactions, 1, 2, 3, 4, and I interleave the operations of these transactions, and I come up with an ordering of all these operations. And if the ordering of that operation can be mapped to, let's say, an ordering of, as if I have done transaction 3, 4, 2, 1, serial order, if I can map it to that, then I can say it's correct. If I can map it to 1, 2, 3, 4, I can say it's correct. So as long as I get, I do the transaction in certain order, I get a scheduled, and I can map it to some serial schedule. The database doesn't impose that has to be first transaction, then second transaction, third transaction, or fourth. It just says you do your transaction in some order, and whatever order that non-deterministically you came, depending on the scheduling of the context switches of the processor, just whatever that happens non-deterministically, probabilistically or non-deterministically, as long as the final product, the final outcome, can be mapped to a serial schedule, then I can say it's correct, because I know serial schedule correct, and as long as it maps to one serial schedule, then I can get correctness criteria. And that it's a very simple and clever model to be able to reason about the correctness of execution. And that gets a little bit more involved. Only I care about transactions that are conflicting. Moreover, I only care about the transactions for which the operations are conflicting. So it gets a little, it gets more complex in that sense. But the idea is this, is that if I were to do some interleaving of operation, and at the end I can say this interleaving can correspond, if I take this interleaving, it does correspond to some combination of serial execution, as long as one schedule maps to some combination or some serial schedule, doesn't matter what it is, 1, 2, 3, 4, 3, 2, 4, 3, 2, 1, 2, 3, 1, 4, doesn't matter. As long as I can say it looks like one of those, then I say the execution is correct. Of course, if I reorder transaction, the outcome is different. That's fine. The question is a matter of correctness in terms of no one step on each other's toes. And if things can be mapped to one serial schedule, then I can ensure that there was no stepping in on one another. So then it's correct. And locking, especially they call two-phase locking. So that's one way of doing it, is a pessimistic form, and just basically says, kind of correspond to this previous slide that we had. If I kind of lock everything, then I kind of get, it creates an ordering. And so then that's one way of doing it. Again, we're going to really go into these depth in the coming, especially I think in February. So I'm not going to go in details, but just a general idea. I can do some interleaving of operation, and as long as that corresponds to some serial execution, then it's considered valid, and it's considered, I can say it's correct. Any questions?
So when will it be invalid, since like every combination is valid? So when...
Not every combination is valid. As long as it maps to a serial. For example, if I have so let's say I have two transactions, and each has two operations, okay? If I do the first operation of the first transaction, then do the first operation of the second transaction, then do the second operation of the second transaction, do the second operation of the first transaction, then do the second operation of the second. So I kind of do the first operations of all transactions and then the second operation of all transactions. So that's kind of an order. But if I do for the first operations, I do transaction 1 followed by transaction 2. For the second set of operations, I do transaction 2 first, then transaction 1, then that's not going to map to a serial order, because for half of the operation, I did this stuff for transaction 1. For the other half of the operation, I did this stuff for transaction 2 first. But in a serial execution, that couldn't have never happened. In a serial execution, first 1, then 2, or first 2, then 1. So that's a serial execution. But once I mix things, for some transaction, I do certain things first, and for the other transaction, I kind of reverse the order, then it's no longer serial execution. And that's what we wanted to avoid.
Oh, okay, I got it. Thank you.
You're welcome. Okay. So this is, so the sort of the space of concurrency and the different optimistic, pessimistic, it's huge. So this is there's a slides. Several of these slides is the book that I wrote last year or 2 years ago. It's called Transaction Processing on Modern Hardware, and it's freely available. You can get it from the course website. There's a link, and if you log in from UC Davis network VPN, then you can get the access from the publisher for free. And so there we kind of looked at all these kind of, so explored in the last 20 years, the different kind of transaction mechanism, whether they're optimistic, whether it's pessimistic, there's blocking, there's non-blocking, there's using restrictive, or kind of there's no coordination, they're using multi-version, the records have many versions, or they're using timestamp. So there's a lot of different interesting work that is done in this space. And we kind of, throughout the course, we will point to this book to kind of, some of the topic is relevant for this course, some of the topic is beyond this course, but it's something to, if you're interested in this topic, this could give you a good overview of what has happened in the last 20 years in this space with concurrency control. And then, so in order to ensure atomicity, one last topic is that we want to do all or nothing. So then what happens if I want to do all or nothing, but then things crash in the middle? And this kind of go back to the notion of the log that we talked about. So if I'm keeping a journal of everything that I'm doing, and if something in the middle crashes, then if I'm in the middle of a transaction and I've partially applied set of operations, after I recover, I can look at my log and just remove or undo those partial operations. That's one usage of the log. Or if I have done set of operation, I've done it I've written it in my log, the transaction were committed, but the changes were in main memory only. They were in a volatile memory. They haven't been reflected into the persistent storage like this, and the database crashes. So the transaction was committed, meaning the user was given the commit ticket, but then the data is lost. So then I can go back to my log and figure out the transaction that needs to be reflected onto the database, and I reapply them. So I redo them. So the log allows to remove the actions that shouldn't be there, also allows us to undo those transactions that shouldn't be there and redo the transaction that should be there. The notion of commit means that if something was committed, it needs to be remembered indefinitely. The notion of abort means if something was aborted, it should be forgotten indefinitely, or at least not reflected into the data. So it has to be notion of permanence in what's commit and permanence in what is aborted. And the log is a simple structure that allows me, or that allows us to be able to keep track of what needs to be redo, what keeps to be undo. And why do we need that? It goes back to that simple idea. The writes are much more efficient to apply it to a log than to the storage, than to the disk. So in terms of the correctness, it's sufficient that I write to my log and I make sure the log is on the stable storage, has been persisted, and then take my time to modify the data and take my time to modify the index, because those are more expensive. So I can finalize the write by making sure it's on the log, but then take a little bit more time to do other things. And but if I take my time to do other things, it's might possible those changes hasn't been reflected on my indexes. Those changes haven't been reflected on the storage, and the database crashes. So then I will have a data loss. So log could be my point of rescue. I can go to the log, and make sure that whatever that was recently logged but are not reflected in the data are redone or removed. So make sure that there's nothing that is missed and there's no side effect. There's no noise. It means there's nothing that shouldn't be there accidentally, partially. It's kind of lingering around. So that's the importance of the log. That's what the log does, sort of high level. And again, the key of it is to make sure that before the transaction is called committed, the log of it is written to disk, so it's persistent. And then two things in the log we maintain. We kind of take a before and after image of anything that we changed. The before image allows us to undo. The after image allows us to redo. And then we also keep track if the transaction was committed or aborted. If there's a commit entry in the log, that means it was committed. If there's no commit entry, implicitly means it was aborted. And if there's an explicit abort in the log, also means it was aborted. So that allows us, the commit and abort decision allows whether we should redo or we should undo the action of a transaction. And again, the log needs to be written on the persistent storage before the commit time. Usually, there are exceptions to that, or there are methods that kind of try to deal with that to relax that as well, but generally we wanted to be able to do that. And that's kind of this sort of the overview, and kind of I'll just leave you with that. So the log was the final piece, especially to ensure the atomicity and the recovery when something goes wrong. So any questions? If not, then have a wonderful day, everybody.